So one of the applications that we have for magnetic fields, and particularly for wires feeling forces in magnetic fields, is for motors. And for a motor, we take the electricity that we've generated. So we've sort of taken a path through elementary physics. We've generated some electricity with turning a turbine, using an engine, and then at the other end we want to turn this electricity into something that rotates. So the way we get electricity to make things rotate, or we rotate things to generate electricity, either way is by the means that we've got here. So electricity, we want to use electricity to mechanically turn things like axles for wheels, to move things forward, to move anything actually. This is sort of the basis. So this is a toy model. This is not the most efficient motor, but it lets us see how this works. So the idea here is we've got current. So I have a battery right here, and it's generating current, and this current goes through these blue things called commutators, are metal, as is this gray stuff right here. That's the brush. It's also metal, and it gives us a current that we see in this direction. So we're going to focus first on this side, on the left side. So that's the direction of the current. We've got a magnetic field because we've got a north and a south pole. That sets up our magnetic field in that direction. So that means that we've got, if we just redraw it, there's our current on this left side. We've got our magnetic field like this. And so if you take your right hand rule for I cross B, remember your I is on your index finger, your B is your middle finger. So you look at the screen and try this. So you point I in one direction, and my tendency is the B, I have to actually rotate my hand, flip my hand, so I can get my middle finger along B when I'm looking at the screen. And so then my force is actually down. That's my force. Okay, so I hope you got that. So that's the force on that one. Okay, we're going to look at the other side now. So this wire that's sort of hidden, so that has a current that's in this direction. That's the direction of the current on the right-hand side. The magnetic field still points in that direction. So again, looking at the screen, take your right hand and make I point towards you, your magnetic field, and then your force in that case is actually up. So that's your force. So I'm going to get rid of all of these markings. Let's practice with the right hand rule. And that gives us then a force down over here, and a force, which they've labeled force magnetic, is up. Notice that for this loop, this square loop, if you like, the force is balanced out, right? On the left-hand side, there's a force down. On the right-hand side, there's a force up. So they balance out. But if we put it on an axis, then this axis, like right through here, then we have a rotation, right? This rotates sort of, that up part comes, the right-hand side comes to the top, and the left-hand side starts to go to the bottom. And so we end up with a situation like this. And so again, we still have a magnetic field sort of in this direction. But if we have a magnetic field in this direction, and we had a current, if we had a current, say, going like this, I, and we have B like this, I cross B, could still have a down pointing force, but notice that's not going to cause it to rotate anymore. And so what happens instead is that right at this point, at this upper point, notice there is, if I zoom in here, a little gap. And so I don't actually have any current flowing right when it is at this 90-degree point. Okay, so there's no current, so the momentum that it had, it can just keep going. So it keeps going like this. And the other thing the gap does is something that's really useful, is that notice over here, sorry, hope you aren't getting whiplash with this changing. This side is connected over here to plus, and this is my minus side, right? That's connected to the minus side of the battery. So that's the direction the current flows. I'm going to just mark this one so we can kind of watch it. As it rotates, that one comes over here, so it's not touching anything. But as it rotates further, notice that if this rotates some more, then this is suddenly now going to head to be my minus side. It's going to be connected soon over here, right? And so what happens is where I had current sort of on this arm, which I'm going to mark with this purple, going that way, now this purple arm, is going to have current coming the other way, so that as this rotates around, as this gets a little bit more tilted over, so we can imagine this is slightly more tilted down here, then this is suddenly going to pick up current in that direction, which will give me, with the magnetic field like this, and current, which will start this now feeling this downward force that we saw over on this side. And so this gap does two things for me. It means when I get to the top, I don't have, there's no torque anyway, so it's not applying anything other than up and down forces, but it also allows the current in this arm, this one that was, the current was, this right hand, the current was going this way, it gets to the top, and then all of a sudden once it crests through the top, the current is going the direction it needs to go, so that I get this downward force to keep it continuing moving. And so we can look at this, and I've already talked about torque, so that should remind you of back to Physics 1. We can look at this sort of in a side view fairly quickly. So if I look at this, once it's kind of crested and has reached the top, say we're like this, I guess we don't have that set up. Okay, so that's our gap there. So we've got our current that is now going this direction. There's I, and our magnetic field is this way. There's B, and we'll say we're at just a little bit of an angle past the vertical. Okay, so we'll call that an angle theta past the vertical. Then I cross B gives us a force down, right? That's our force down. So if I look at this sort of edge on, I have a force down. Now only one component of that force is actually going to cause the rotation. It's another cross product, right, from the torque that gives us the rotation. If you remember, our torque, the magnitude of the torque, was R times F times the angle between them, sine of the angle between them, or what I call the perpendicular component. That would be this component of the force that's perpendicular to this moment arm right here. So this moment arm is like, if this is a side of length L, this moment arm is L over 2. The force is, of course, from I, L, the long length. I guess I'll call this a width. Okay, width, so that's the width, times our magnetic field, and then this perpendicular force, oh man, sorry, there we go, this is, if we look, then the angle that is between these two, if this is an angle theta, this is also an angle theta, so that's sine of theta. Or you can see, in fact, that this component, if this is theta, right, then this component is F sine theta. This sort of purpley component here, up here also. So that's the, yeah, this is not a great, that component. It doesn't look like it's sort of going downhill to provide the torque to twist it around. And so, but that's the component of the force that helps provide the twisting. So we can find the torque, and then from that we could find what the angular acceleration would be. Now this torque is going to change because we get different components of the force depending on what our angle is. So it's not an easy thing to calculate, but at least we can get the idea of how much torque we have as this rotates and goes around. So I just wanted you to see this connection really between the torque and that we learned back in Physics 1. We can go back to forces, but in fact, the useful thing is figuring out how this continues to rotate, and then that rotation can translate to axles and wheels rotating, to things moving, gears moving, and doing any of the motion that sort of keeps our modern life going, as it were. So this is just an application. Really what I want you to take away from this is that you can practice your right-hand rules and checking that you know the direction of the